Good morning.
You. Psychology.
Morning from Forge.
Good morning from North.
Good morning. Is King George out there yet?
Oh, and you see the jam. So mean.
All right. Well, we do have a limited amount of time. Oh, hey. Good morning, King George.
Good morning.
Hold on 1 second.
Pardon me there. Good morning, I'm Mrs. Crescio. We're going to do the next section of differential equations, solving differential equations. So hopefully you have this packet that I'm showing up on the monitor here. I want to start out with going back to the previous section of solving differential equations and the applications that we saw with exponential growth. So I have at the top, you have your given formula here for an exponential growth differential equation. We just looked at that in my class with some examples, but we do know after some calculus and essential calculus steps, we can solve this through separation of variables and finding a c value to get a solution to the differential equation that shows exponential growth. Okay, I was telling my students that you can memorize these two formulas as this differential equation will always solve to this solution, but really on an AP style test or question in a class or in homework, we want to show all the steps to get there. We do have on that monitor on the left-hand side a slope field for the exponential growth. So I want you to look at it and reflect. What do you see? Do you see how to sketch the solution through the given point? And I see that my point here at 0, 5 has some slopes that indicate growth on the right, and then on the left, as I go backwards, looks to me like I have a horizontal asymptote in the slope field. So a horizontal asymptote, well, in calculus, slope equal to 0 is really a derivative equal to 0. So where do we see where that derivative is equal to 0? We see that horizontal asymptote at y equals 3. Now I'm going to point out that this is really key to knowing what type of both solution you might see as well as what type of sketch to draw through and why to explain it that way. That y equals 3 horizontal asymptote means that the derivative, the differential equation, is not going to be just like the one that I have at the top there. It's going to be slightly different. Instead of just having a k times a y, we're going to have a k times a elevated y. And so we'll see it with like a factor situation, y minus 3. Okay. Again, the slope field shows us lots of different things. It also shows us that we see an exponential growth. And we see the solution in the slope field. So now relate that to the slope field that I have on the right side. Do you see asymptotes again? Do you see slopes equal to 0? And I can see this right here through this region. It looks like my slope field levels off to 0. But I see a second one. When you look further, when you look through the slope field from top to bottom, does anybody also see the slope field leveling off to 0 there? So I have 2 asymptotes, 2 values where my slopes are going to give me a 0 or a horizontal slope. That should maybe lead us to think that the factors in the differential equation is not just a single factor with one horizontal asymptote, but we actually have 2 horizontal asymptotes, one at y equals 0 and one at y equals 3. But I'm going to point out something a little bit interesting. This is not the same factor on the exponential as it is on the second graph. And let's sketch the slope field just to see why or how that might be slightly different, just slightly different. So through our initial point, given point, we see our slopes maybe go up and level out to the right, and towards the left also have a approaching 0 at negative infinity. Does anybody remember this sketch from a previous class? I'm going to throw this out there.
Inverse tangent?
Can anybody else see that this is similar to an inverse tangent? Yeah, similar looking with the 2 asymptotes, good. What if I said environmental science? What else might be seen with this in an environmental science? And I have someone over here, Marcus, what is it? Logistic, oh, that's what I have on the paper. What is that? What do you recall about logistic growth? I mean, no, seriously, did you call it logistic growth in environmental science? Say it, Tyler.
Carrying capacity?
It's a graph to measure population over time with the resources given in the habitat.
Okay, so in environmental science, we had the population curves. I don't know, I think Ms. Pogue at our site called it an S curve. Yeah. Okay, we don't call it an S curve, but it does reflect on our population and our growth and our capacities. Do you remember the limiting capacity or the carrying capacity? So that's what this is. This is the math behind what we see as the logistic growth curve. And so we're going to look in depth at this. On that paper, the whole bottom of the paper really has all the essential ideas for you. Right next, below this, we have, I've given you the 2 formulas, the differential equation formula and the solution formula. And so the differential equation, like I have above, is going to look like this. We see 2 factors of, and typo here, sorry, this is supposed to be a capital P. We see 2 factors of P. Our derivative of our growth of our population has 2 factors of population on the right-hand side. And in my example, I had 3 as my L, where my L is seen here. This is what we know as the carrying capacity. That top asymptote, where we level out. And K in my above problem we didn't identify what it was, and so we might be able to find it, or we might be given a k value. In the solution, now the interesting thing about these two equations, just like above at the top of the paper, the solution to the differential equation is a bear, and the calculus to get that solution is really heavy. So you can always look in your textbook at the, the derivation of this particular solution or this general solution, but it's really difficult to manage, and from everything I've heard and read, we're not expected to do that calculus between those two equations. The calculus that we are expected to do is we need to just know this, know and memorize the formula in case we needed to apply it. But more importantly, on this page are all the things we need to know in calculus. We need to know how to find the limiting capacity, the carrying capacity. We need to know in this second bullet here that if we have a limit over a long period of time, so if we have a limit as t goes to infinity, the capacity is the limit of our population. And so if you see a limit as t goes to infinity, really don't be afraid of it. It's just that end of that asymptote all the way over to t equals infinity. Also, in addition to that, if you look at that growth curve, I just need to sketch it again down here, that logistic growth curve. And we have 3 on our growth curve above. I just need to rewrite it. We also need to know that if you look at that curve and we're asked a question like the next bullet that says, when is the population growing the fastest? That would indicate the inflection point of the curve. And it doesn't matter if my curve is shifted to the right or shifted to the left through any initial condition. Any logistic curve, the inflection point is always going to be at halfway of the carrying capacity. Always. So if I state the carrying capacity is 3, I can then reflect that the population is growing the fastest at 3/2, or 1.5. You can find this, though, if we actually had to find this. What's an inflection point come from? Second derivative equal to 0. And if we know that we've been given the first derivative as our differential equation, we can always find the second derivative and set it equal to 0. When we do this, we're going to get a p-value. We will not get the independent variable of time. So when we solve for this L over 2, this is a y value given to us. It's y equals 1/2 or 1.5. As well as the fact that when I solve this second derivative, we're only going to have p's involved in our equation. So finding t might be a little more difficult, but finding the y value of the fastest growth rate is very straightforward and simple. And then an additional thing, we'll see some examples. This form I give you on the paper on the front page is the preferred form for all of my problems, just because I can find a really quick carrying capacity in this form, as well as I can find a growth rate, and I can use it to plug into the solution. All right, so see some examples in action. I don't know how much I'm going to get through, but I'm certainly going to allow my kids to keep going and use some of it as homework. These are all fairly straightforward, but they're straight from AP resources. So we have an example here. I just want to show you that in this first example, I've given you a differential equation at the top. However, I've also have 3 down the side. And the 3 down the side are the exact same differential equation. Recognize the similarities between them. In addition, recognize that the one that I highlighted on the front is in this form. With the dependent variable of p, that's my variable, so that's going to be our variable everywhere. L and k are going to be numbers. And in this form, it's the easiest to pick out on the page. Which one is it? It's not the top one. Doesn't look quite the same. Which one of those in that list looks most similar to my desired form? The third one down? Or, well, the middle one right here? And so from factoring, we can set this 0.02. If you don't know your fractions, 0.02 is 2/100ths, which is 1/50th. We can recognize that those are similar. We can recognize that the first one and the last one have no factors, and we may need to factor out. So on both that top and the bottom one, I want to point out that we're going to want to factor out at least one of those y values. And not just factor out one of the y values, but I'm circling this here so you can see it. At the end of my second growth factor, I want that y value to be isolated. So I'm going to factor out a y over 50 from this bottom problem. Now by doing that, my back of my parentheses, the factor in there is going to be just a single y like I want it to be. But when I factor that 1/50th out of the initial y term, that's going to be just a plain 50. So they all adapt with, you can always distribute back in. If you're not too sure, did I divide or multiply correctly, go ahead and distribute it back in to make sure you can match it up. But in the one green at the top, we have our p-value as our population variable. Our L is 50, which we see on the growth curve on the slope field. And our K in this case was 1/50th. So that's a rate, a percentage rate for K. And then sketching through the initial condition, y equals 10 when x equals 0. Go ahead and sketch your slope field, your particular solution. And when we were in class the other day, we were talking about Euler's method as actually just step by step making this sketch, but with numerical values instead of a graph. I also think of this kind of like that new show. What's it called? Where they drop the ball through the thing. It used to be called Plinko. There's like a ball and it's the wall, I think it is. Yeah, that's the way I think of the slope fields. Right, so I have a particular solution. What is the carrying capacity? Oh, okay. So the carrying capacity is L equal to 50. And for what value of y is the function growing the fastest? 25. I do want to state that the function is growing the fastest at half of L, or L over 2. I do want to put that in there. Fastest growth at half of carrying capacity. Because if I don't show the second derivative and set it equal to 0, I haven't really done any calculus. We can't just expect to get full credit, especially with AP points. We saw lots of free response, especially with the midterm. In order to get your points, you do want to have some calculus in there. What is the growth constant? Oh, I already just answered that to you above. The growth constant is 1/50th. And then the bottom bullet is really the heaviest amount of math, although not calculus. We're now going to determine the solution using the initial condition. So this is where knowing that formula from the front page is essential. Our solution formula is, in this case, y. And I have y as a function of x. Might be p as a function of t, dp dt. Is L over 1 plus a e to the negative lkt. And not t. In this case, we have x. So I can plug in, and I do know I have k and l. The missing value then is a. And a comes from our initial condition, which is x equals 0, y equals 10. So I'm going to use all of my values, and what I'm left with when I plug in all the known values above, I'll see that a is the only variable, or the only unknown. Oh, hold on. When I plug in 0 into e to the negative lkx, I'm going to have a 0 up there. Again, the initial condition is really important. So lk, I'm not going to deal with that just yet. Let's just find a. Lk zeroed out when I plugged in x equals 0. But we have the idea that we can take the unknown from the denominator, and we can multiply to the left-hand side and then divide 10 on both sides. So in bringing our equation into something where I can solve for a, it's like a proportion. And then we can see really quickly a is 5 minus 1, so a is 4. So I'm going to go back and I'm going to use that. I use my initial condition. I'm going to plug it back in so I get the specific solution. And now I'm running into negative lk. Well, if I can just do some quick math with my L and K from earlier, LK is just reduces to 1, so this is a negative 1 times x, or negative x. Again, I want to point out very little calculus down here because we didn't separate, integrate. We integrated partial fractions, all that. It would have been a lot more work than just evaluating for our known formula. Oh, sorry. Are there any questions? Can I specify on anything here? A few more questions that I have listed are things, multiple choice style questions or very short answers. The next example is about moose in a national park. And this is more like what you learned in environmental science. So I have a logistic differential equation, and I see that not only did they tell me it's logistic, I can see right here, logistic because I have two separate factors. And I have an initial condition, and I'm asked, what is the limit, typo, fix this please for me. This is t goes to infinity. As t goes to infinity of m. So I'm asking you for, what do you think this is indicating I should look for? The carrying capacity. The limit at t approaches infinity. And so we have the curve somehow comes up and hits our carrying capacity at infinity. So can you tell me what the carrying capacity is? Not in the form that I had where I could isolate L and K easily, but can you all identify that it is going to be a carrying capacity of 200? Yeah, it's pretty clear to see it in there because it's m divided by 200. So I'm going to rewrite that so that that second factor only has m and doesn't have divide by 200, which means I'm going to have to factor out a 1 over 200. So 0.6, factor out the divide by 200. And if I factor out a divide by 200 from 1, it means the 1 inside of our parentheses turns into a 200. So the solution to that first question, the limit as t approaches infinity for our moose population, is the carrying capacity of 200. That wasn't necessary to factor to find the answer to this, but the second question there, what is the solution to the differential equation, goes back to saying, well, now I need to use my differential equation and put it into a solution form now. Solve for the logistic growth function. So I've figured out my L is equal to 200 already. I'm almost there. I'm not too far off. L over 1 plus A e to the negative LKT. So we're going to find A again with our initial condition, but let me look back at this and say, well, what is LK? Because LK is certainly going to have to be in the equation. K is 0.6 over 200. It's the constant in the front. So yeah, so if I multiply K by 200, I get 0.6. Don't do the extra math, just evaluate, distribute in a quick sense. So I can use that as my LK for my exponent, but let's plug in our initial condition to find A. 0 using 0, 50 for P and T. And I'm going to let you guys work that through just like I did the other example and see if I can get somebody from a site, one of the other sites, to tell me what they get for their A value.
We have an A value here at Forge. Is it 3?
Yep. Everybody else get 3? All right, good. Thank you. So we get A equal to 3. And I'll let your on-site teachers specify how to do that if we need to. So now I can put everything together and I can put it all into my general, go from my general equation down to my specific particular solution. So I have my particular solution using my initial condition. And we just identified LK was 0.6. So there's our solution. Much calculus? Not really. Please don't be afraid of that limit. The limits here are extremely easy because all infinite limits are about end behavior, and it's really easy to identify end behavior for these types of problems. So try this multiple choice, and we see we're given 5 options and a graph. Now on the graph, the easiest thing is our carrying capacity. So the concept on the multiple choice question is, do you know which of the following is logistic form and logistic growth? And I use a method very often here of eliminating what I know is not logistic growth. Here's one of our desired forms. I'm pretty sure you can see really quickly with me that E gets cut out. Now, why is there a negative? Why does a negative have to be in that equation? Because it represents the factor of the zero that would be represented when I let 200 minus P. If I let P equal 200, my derivative would equal a horizontal slope equal to 0. Slope equal to 0 there. Then I go back and I look at the other ones, and they're shifted. P squared in the front or P squared in the back. And if we look at the form that I have, P squared should always have a negative attached as its coefficient. It should be a negative term. So we can eliminate C and D that way. And then finally, looking at the other two, it's a method of factoring. If I use that idea that I used before, where I want my term at the end to be just a plain P, I need to divide by 0.001 in this first term. So I'm going to take the 0.02 or 0.2 and divide by 0.001. and 0.2 over 0.001 compared to 0.1 over 0.001 in option B. 200 and 100, so my answer is going to be A. The carrying capacity in A can be factored out to be the 200 we need. And again, sometimes I say, well, wait, did I do it right? If I'm not sure, redistribute. Free response from 2008. The last time we saw a logistic growth question was in 2008. And calculators not allowed. Yeah, they come and go. We don't ever know if we're going to see it from year to year. This is a logistic differential equation and a slope field. Love slope fields. Be careful because in this differential equation on the slope field part A, they gave us 2 points to evaluate slope fields for. So our slope field for the first point in there, 3, 2, I can see that that point lies within the S curve, lies between my two horizontal asymptotes. But what about that other point? Right, it ends up above my top asymptote, above my carrying capacity. And in reality, what that means is that I have too much in the population and I can't support it. So people, animals, plants, whatever it is, they're going to decline because not enough supplies are available to sustain the population. So yes, our population has to decay down to or decline down to the carrying capacity. All right, I can see that we're kind of running up against our travel times and the end of the broadcast. I see that Euler's method is in here and a particular solution. So it follows on with some of the topics that we've covered already in this broadcast here. Again, thanks for coming in, and hopefully you on site can pick up some stuff and get through this.
Thank you.
Thanks. Have a great weekend. Thank you.